Okay, so what is the whole picture of our vector field look like? Have our inclines and linearizations. We'll just write down again what the vector field was. It was 10x minus 5xy, 3y plus xy minus 3y squared. So first off, we'll draw in the nullines. Well, we'll start off by drawing an x-axis and a y-axis. X-axis, y-axis. We draw in the nullines. So the y-axis was a place where x prime equals 0. Actually, first thing I should do is draw in my three equilibria. That. So this is my three equilibria. Down there, up here, down there. The x-axis was also a null incline, this for y. So here y prime equals 0, and it was going out and out. Y equals 2 was a null incline for x. And my arrows are going down. And they switch to up over on this side. And y equals 1/3 x plus 1, which is the line through these two equilibria, was the other null incline for y, and that comes down here somewhere. And my arrows were left up here, right in here, and left out that way. So there's my null inclines. Then we want to add the linearizations. At 0, 0, we had things going out, and our linearization had other solutions looking like this. At 3, 2, it was a spiral, and now we know which way the spiral is going. Go up, across this horizontally, down, and back into that. So we're going that way, spiraling in counterclockwise. And then here, we have to be a little bit careful. The slope of this null incline is 1/3, but the slope of the eigenvector was 1/8. So we had an eigendirection like this, which was going out, and this was a saddle. Things come in, cross that way, oops, go out, come up and go out, come up, cross there and go out, and go down like that. And so there's our picture. So again, remember the nice thing about null inclines is that signs of the arrows, signs of the components only can change at a null incline. So all my arrows up here, for example, right, this is 2x null inclines. All the arrows up here are pointing to the left, right? And this is a y null incline that's bounding this area. And in there, all our arrows are pointing down. So all the arrows are here pointing down and to the left. Likewise, in here, we know that arrows are pointing up and to the left because everything is spiraling. Here, everything is to the right and up and down and to the left. So in this area, we have spirals going this way into the origin. This particular trajectory, the one that comes out along the eigen direction, when it comes out into here, it's going to have to cross this going up, cross that, going across, come back, and go up. And remember, one of the things about solutions is you can't cross solution curves, right? And we have a solution curve here, and here, and here, and here, and the x-axis. And now we have this solution curve. So any solution curve coming out of here has to come up, can't cross this curve, go up and around and in. And curves here would have to be trapped between those two. One out here would go out and up and around and in. These come down and around. Right? So everything in this first quadrant is, in a sense, coming from here and wrapping around and sliding into there, except for this one trajectory that's actually coming out of the saddle. Down here in the lower right, we know that everything is pointing down and to the right, so everything just sort of continues like that. Down here in the lower left, we know that in this area, everything is going down. This is a y nullcline here, and up there, everything is going to go up. So our solution curves are coming down out of that. They'll hit this line and start coming up, but they'll never cross the x-axis again. Whether or not they actually are asymptotic to the x-axis or not would require some further analysis, which I'm not going to do. So down in this area, well, if we're starting in here, we'll come out, we'll hit that, and then we'll start coming down again like this. And there's one particular one, the eigendirection here, that's going to come out, just slide along like that. Now, up in this area up here, we don't know what the sign of x prime is. We don't know whether they're going left or right. So x prime equals 10x minus 5xy. Here, x is negative, which will make this term positive and this term negative. As long as y is bigger than 3, this term will be bigger than this term, and so we'll actually have a positive x value, and our arrows are going down and to the right. So these solution curves come down and then out like that. Right? They keep going to the right till they get hit there, then they cross over and go to the left. And so there is our sketch of our vector field. So separatrices, there are some solution curves called separatrices that are important. In this particular one, if we set up our picture again, what did we have? 3 equilibria, those are always super important. We have a solution that runs out from this equilibrium to the right, and one that runs out from this equilibrium to the left, one that runs up from this equilibrium to that one, coming down to this equilibrium, coming out of that equilibrium. And so those are all very important things because those are solutions, and we know that the other solutions can't cross them. So these are called separatrices because they're anchored to the equilibria or to infinity, and they form boundaries for the other solutions. Now we had 2 others coming out of this one. There was an eigendirection that came out and then wrapped around going out this way, and then out here there was the other eigendirection that goes out this way. Right, and so that's a structuring of our vector field, right? Sort of a skeleton for it. What the other vectors solutions do are restricted by this selection of vectors. And these are called the separatrices because they separate the solutions to the vector fields that can't cross these. And they usually go from equilibria to equilibria or equilibria to infinity or sometimes infinity to infinity. And there are other cases that we would want to look that are possible. But they restrict what your solutions can do. So then we're going to look at this on GeoGebra and Excel and see how that helps.